Caglayan from Tampere University, Finland. Let's welcome Professor Caglayan.
Thank you. Thank you. Share my screen. Okay, I hope that you can see now. First of all, I'd like to thank for the invitation. I think it's really nice to introduce some of our works to the audience in this symposium. Of course, I think everybody would like to meet in person, and I also would like to see Indonesia, I guess, but this is what's in the situation. But again, thank you, and thank you for the attention. I would like to talk today light matter interaction with multi-layer epsilon materials. Actually, I would want to talk both about the linear and the non-linear aspects of this material, but within the time constraint, I think I'm going to focus on linear ones, feature like more detail here. Yes, just one slide where I am located right now. So we are in the quite north region of the world, and this is where Tampere is. This is the capital, and we are a little bit inland. And our campus is here, located in the Permittivity region, and this is where we lab and offices here. So just before that I begin the light matter interactions, I would like to mention that it's a great place also to see some fascinating light matter interactions also in nature. So strongly recommend the area. And this is where we do most of our measurements, characterization measurements for the linear case and the linear applications. Some over there. But let me get back to the topic. I wanted to begin with this introduction because I'm not sure if everybody is familiar with Epsilon-near-zero case. So when we talk about the materials and material properties, especially from materials and metamaterials, we have mostly focused so far is epsilon very large, permittivity very large cases, and the permittivity is much larger than the materials that we usually use. And those are somehow good for if you're looking for such as like a scattering application or sensing applications, they might be quite useful. So there's another opposite to this, where we have this epsilon permittivity getting closer to the zero case. And this is today's topic. So these materials are, yes, where we have the permittivity getting closer to the zero. And it is possible to find actually some of them naturally occurring, especially some of the transparent conducting oxides, such as indium tin oxide, aluminum oxide. These are nice ENZ materials that are working in the near-infrared region. Maybe it is better to just point out here that, so this is, for example, an example of aluminum zinc oxide. So this region, where it is defined as like here, defined as this area. So we can consider this area as the ENZ region. In this region, it's not only that real part of it is getting there, also the imaginary is quite close. And this is the example from indium oxide, and again, this ENZ region is around 1.4, 1.5. But there are other examples, of course, such as silicon carbide, which is very nicely as a material around 10 micron. There's gallium arsenide, 8 micron, and there are different materials emerging every day, such as this one is kind of organic ENZ material you can size, for example. Also, one can argue that metals actually zero crossing, so they might be considered as well as easy, but just one that the imaginary part is that low. That's one problem. And then you see here that we have some options in the near infrared, far infrared, UV, and such, but we don't really have much opportunity for these materials to find in the nature that are looking in range. There's a gap for that. And actually, one can also structure, if you cannot find this in nature, one can somehow bring materials together and structure, make a metamaterial way to get these ENZs metamaterials. One way, which is most common way, mostly used way, is stacking metals and dielectrics on top of each other. This one, of course, wouldn't give you a homogeneous permittivity. But in one direction, it will act effectively as a near-zero case. And this kind of structures have been studied as called hyperbolic metamaterials. That was the first idea with stacking of the case. But we also know that this can give us some region as well. And today I go mostly on this kind of structure. Another option, which I'm not going to get into any detail of this, is to operate a waveguide at its cutoff node, and then this will give you the region inside the waveguide. That's a story. So these are some of the properties. And this is why it has been quite interesting for many years that these materials has been studied. They can provide supercoupling. They basically stretch the frequency. So what happens is that you stretch the wavelength when permittivity gets close to zero. Index gets close to zero. And so index will get closer to zero. Change the so for the number high phase velocity, some of the examples that also find some good applications with these materials. And you can find reviews, but two examples you can find. Again, there is also one recent study that has been proving on this topic, is the enhanced non-linearity. It has been studied also recently in our group and Robert Holt's group in Canada as well. And today, as I said, I'm not going to touch into this much. It has been also a question to enhance the linearity and control also the modulation, speed modulation. Like in the previous case of the niobide, we can also use materials and then modulate electrically as well, and also get this is one of our recent studies, which has been published at the end of this year. This is not been much studied, those kind of materials, but I just want to highlight here. We can find more information in this paper. We can also get rid of some phase similarities using these Epsilon-near-zero materials. So that's why it might be interesting for some applications. If there's a similarity, want to remove that similarity, that's a good option as well. And then we have shown that also experimentally in this work. Okay, let's get back to the work. So what we really did. So what we really did in this study is the idea of bringing these hyperbolic materials, and we use these hyperbolic materials, which is basically that stacking of metals and electrics, and we obtained a visible effect. So we did two kinds of stacking. and one of the and call them HMM1 and HMM2 just for the sake of clarity, because this kind of structures used to be called HMM, but actually this is my both of my ENZ structures. First, what we did is we used 10 as you can see, cross section of the SCM over here, Untitled Chapter stacks. The other one, again, we kept the gold the same, and then just changed the thickness of the titanium. When you look at them effective working, then you can see that we have two different wavelength and region, and both of them actually falls in visible region. One being around 680 and the other 750. So we can also even go different, a bit of close to 600. Even this studies was optimized based on some constraints that we had. Anyway, so this graph over here shows both the transmission reflection that has been obtained. First, HMM1 over here, and the other one is HMM2. And here is the calculation, just known as Maxwell-Garnett effective calculations. Basically, what we use in these kind of calculations is that just average. So you have a metal permittivity, dielectric permittivity, and kind of you just use that based on how much the thickness is. You bring them together and just take the average. And this is what it is in this case. So let's look at what we have obtained. So for this first case, HMM1, which has been shown here, this real part, this solid over here, and HMM2 has been shown dashed. The real part of this actually is getting 0, around 680, the other one is so there. When we look at the transmission and reflection cases, we can also say that these are working as this. This is another way. This is another sample, just looking again in a similar wavelength ranges. Just I want to show you a closer SCM over here, the cross section, and just want to emphasize one more thing. So here we have both experimental data. The data that's calculated from the simulations, which I just put here as FDT because it's being used that we used numerical activity calculations. And then there's one more here, which is so-called TMM method, transfer matrix method. And we also see how it really works, how combined they are. And it seems like they are quite similar to each other. In that case, we would also like to have this TMM approach working because of this reason actually, because using the inverse transfer matrix method, we can actually use what we have obtained from transmission reflection data and convert it back to the permittivity. So in this case, for example, what we did, measured our transmission reflection, and then used inverse transfer matrix method, which we know that's working. We calculate our permittivity. It shows us that what we expect is what we are really getting. So in this case, this is around 600, just to show that you can really tune it from 600 to 750. Okay. Now I hope that I introduced the Epsilon-near-zero materials and metamaterials, how we get them. Now I would like to a little bit focus on how we really want to use them. One of the known studies is, I think it's been now quite known with many applications, is plasmonics. Plasmonics main localized surface plasmons have been used for many different applications, and people has been studied the effect of the antenna on nanoparticles, considering different sizes, shape, material, periodicity even, and they have shown how they change and how this is affected. I think one of the areas which is overlooked is mostly the substrate and how it affects. Of course, if it's a synthesized nanomaterial, maybe that doesn't concern, but in the case of especially when you have them on a substrate, like a nano antenna case, that's quite critical as well. Mostly used silicon dioxide or silicon dioxide substrates. And in really two cases only, this is our study, and this is from Nanodisks, which has been used at thin layer of metallic substrate. In your case, we also used a thin layer under the dielectric layer over here. So basically, the control of the plasmonic structures with the substrate has been studied much, really. So one can ask then, what we're gonna do? I mean, what if okay, you can put antennas on glass like silicon dioxide or your ENZ. So what really happens? Let me show you what happens over here. So when we have it in the normal case, like a silicon dioxide case that we usually have, people do. This is the image of the electric. On the other hand, when you put it on the ENZ substrate, you completely change how that works. And this might be quite useful for some applications, but I will get to that as well. But I hope that now you consider and that this is a quite effective way. Let's check also this data. These are also simulations where we showed like changing slightly how we can modify how the electric field is distributed and how we can emission fraction. Basically, whenever you go from 2, which is also dioxide, you go to this ENZ and modify the electric field quite drastically. So what we did to show this is we fabricated some nanodisks that are working really nicely, plasmonic elements. To control this, to show this, we fabricated different periodicity, but also we fabricated different diameters. And as you may guess, we fabricated them on our multi-layer structures that I just showed in the beginning. This is overall the schematics here that you can see. So we have this substrate over here, yes, but we have the ENZ medium here, which plays the role. Okay, let me get to the data that we obtained. That is quite interesting over here. So when we have them on the glass and when we change the diameter, as one can expect, so whenever we change the diameter from a certain value, in this case from 120 nanometers to 180 nanometers, you can see that this plasmonic resonance is changing to the higher wavelengths as we increase it. And by the way, this is the simulation. This is the experimental data. Yet, when we put them on an ENZ medium, on an ENZ substrate on top of our HMM1, let's recall that is working around 680 nanometers, in the experiment. In this case, those resonances, they're all fixed to a certain resonance wavelength. And this is more obvious, I think, this experimental data. But in the glass case, they are changed. And in this one, they're always at the same wavelength, just that is 680. And that we call this, it's a pinning effect. So whatever you do, change the dimensions, you cannot really change the plasmon resonance. Another one that, because we can change the ENZ to any wavelength in the visible range. So we just use the other one. And now we see that we can shift it to the other ENZ wavelength region. Now we have all the resonances changing, but shifting, pinning at the ENZ region. So in this one, I would like to also summarize, maybe a little bit showing you how comparison each other clearly. Again, this simulation, this is the experimental data over here. So when we have it on the glass case, you can see it on the green region. By changing the disk diameter, we can see the spectral shifts. On the other hand, when you have them on HMF1, which is designed specifically for the pinning resonance, you can see that the shift is quite minor and can pin the resonance at a certain wavelength. And there's also some small change. One might be at best. I think maybe this change over here. Yet we have this data here. I think for the HMM2 as well, we have quite low shift over here. So I hope I convince you that this pinning effect really works, but I also want to explain you what really happens there. So when we have a vanishing refractive index, meaning that when you have an epsilon-near-zero medium, so you have this an effective, that means an effective medium surrounding this nanoparticle or nanodisk case is vanishing. And usually we find this resonance wavelength as this formula. This is quite known formula, which describes it depends on the effective dimension of your nanoparticle, this diameter in our case. And this delta over here is just field that are going a little bit behind the disk diameter. And as you see this one, if you would have just an effective as 1, 2, whenever you change this diameter, expect that resonance wavelength to just change. But in our case, when we have this closer to 0, we compensate the shift. So we pin the resonance and we go beyond resonance, beyond the wavelength. I think I have much limited time. Let me go further. So one of the ideas that we presented using this is to control the wavefront. So it's quite popular nowadays to use metal surfaces and to control the phase front using plasmonic elements. There are challenges in this case. Either you want to put any element in a certain region, or you want to control the phase differently, and you need to make a really precise fabrication. Our idea is, maybe you can say, twofold. One is that with this idea of the pinning, you can actually get rid of some of the fabrication effects, because whatever you fabricate, you can fix it. You can use it for that. The other one is that you can actually arrange it such that you can put many elements and change the phase using the substrate. This is just a comparison of the wavefronts phases. So here, this is our disk, and this is the phase and how the phase is going towards it. Let me go through the previous A and to H. It's quite messy slide. So in this one, we have this A case, our nanodisk with dimension of 120, the smallest one. Is actually one, also the largest disk. This is, they are both on glass. So we expect this difference, right? The phase should be different. We are looking at them at the same way. In this case, we are looking for the ENZ 1 case 6A. For the CNT, we put them on the HMM, and then we can see that this shift is quite less compared to this glass. And this is the same thing. F glass, which is the HMM2. We are looking at this HMM wavelength here. You can use it to design and control Wavefront. You can make, for example, different substrate regions, or you can use it to control the defects through this Wavefront Control. So what is the take-home message over here? I can say that we can use also ENZ substrate, which can provide better control on the plasmonic resonance and as well as their Wavefront. And you can find further details on this published results paper. With that, I would like to thank my team, and in this study, mostly Mohsin has been completed, and I think we have some tired members also working on this. And I would like to also thank our project agencies, especially Horizon 2020, European Research Council, and you can of course find more details on our website and Twitter accounts. And with that, I would be happy to take some questions. Thank you.
Thank you very much, Professor Caglayan, for very interesting research on the interplay between the Epsilon-near-zero material and localized surface plasmon resonances. Now the floor is open for questions.
I think there are some questions. Try to answer them. Okay, let me start from the last one and I go through. So I think the first question, in your HMM system, what is the role of the height of the nanodisks? Good point. Actually, in our system, we didn't really pay much attention to the height of the nanodisks, because height of the nanodisks may change the resonance wavelength of the nanodisks, but not much. Mostly what changes is the diameter of the disks. I mean, as long as you have quite some thickness, nanodisk, let's say from 30 nanometer and above to 100, they usually stay same. Cannot really change the resonance wavelength of the nanodisks. Therefore, I mean, just choose the height that is easy to fabricate. So in our case, it's 60 meters. We have some cases where we studied 40 nanometer and 30 nanometer, but more or less the resonance is the same for the same diameter nanodisk. And yes, so in the slides, I think the other question is that for two-dimensional periodic structure, how was the spectrum measured? Okay. I think we're talking here about those nanodisk samples. Yeah. So in this one, yes, we measured the transmission using a normal illumination. So we don't have any illumination. It's coming from the surface and not structures, periodic structures, as well as it is to the surface, the ENZ element underneath. And how far deep should Oh, I think you want to learn about what if we put on top layer, such as water. That's a good element. All of our cases, we use air as the top layer. It might as well change to have it when we have the water. Probably that having the water will change the ineffective as well. But in the ineffective case, actually, the medium, top medium, may change only from then 1 to 1.35. That is not a lot of difference, just 0.35. I think that might change maybe the shift a little bit, but I don't expect it to be much. But that's a good question. You can look at it as a suggestion. Thanks, Rahmat. Thank you.
Thank you. Yeah, is there any other question? If not, let's thank our speaker again.
Thank you. Have a nice seminar. Thanks.